To introduce Dr. Fabiane Trindade. She's also postdoc from Methane to Products Division, Project 12. And she's gonna present us today tuning of shape, disorder, and oxygen vacancies in lanthanum-doped Ceria nanoparticles for the oxidative coupling of methane. Thank you very much, Fabiane. The floor is yours.
Thank you, Fabio. So hello, good afternoon, everybody. So my name is Fabiane. I am postdoctor at Division 3, Methane to Products, based on University Federal of ABC. So today I present some of my results on tuning of shape, disorder, oxygen vacancies in lanthanum-doped Ceria nanoparticles for oxidative coupling of methane. First of all, I would like to introduce the team that have been working on Project 12. So Sergio and Renata, they are PhD students. Bria Sisi, she is undergraduate students, and then the professors Daniel Florio and André Flauto. And then also Fabio from IPEN is collaborating with this project. So this is the outline of my talking. I will briefly introduce the methane scenario, OCM reaction, and why we want to design in catalysts, the main challenge involved in this process, methodology, results, conclusion, perspectives, and the acknowledgements. So first of all, so due to the advancements in technologies of natural gas extraction have brought back the interest in indirect conversion of methane. So here we focus on oxidative coupling of methane. That is a road that methane is converted in just one step to ethylene. So, but most of the direct methods, such as OCM, is still in development, and the 30% of yield is necessary to commercialize it. So the biggest challenge involved in the whole methane conversion is that methane is a very stable molecule. So this schema represents the OCM reaction in a metal oxycatalyst. So first of all, the methane activation involves the abstraction of the hydrogen molecule from methane to produce methyl radicals. And these methyl radicals are coupled in a gas phase reaction to form ethane. And then finally, they hydrogenate to form ethylene. So studies have strong evidence that this mechanism can be described by the Marsden-Krevlin. So where the oxidation reaction proceeds through the lattice oxygen of the catalyst. So I can list here a lot of challenges involved in this reaction. As I said, it's still not commercialized. So, and then the biggest limitation of this reaction, the biggest challenge that we still study very hard to overcome this, is that the first part, the activation of methane to produce these methyl radicals, this is more favored to form CO and CO2 products. So here, this part is very important. The catalyst can be very selective and control this oxidation to form the desired product that is ethylene. So to overcome this challenge, so we propose here to design a catalyst by controlling the morphology, the oxygen vacancies disorder to improve the OCM reaction. So in our work, we produced a controlled catalysts, nanorods and nanocubes by a hydrothermal method. So to control the oxygen vacancies, we doped these catalysts with different ratios of lanthanum. And then why we chose lanthanum as a dopant? Ceria and lanthanum have different valences. So this results in defects in the solid solution, Ceria lanthanum solid solution. And then also lanthanum has a good basicity that is really important for OCMU reaction. So in this, as I said, we controlled these nanomaterials by changing the temperature synthesis 110 for nanorods and then 180 degree for the nanocubes. But after up to 20% for the Ceria synthesized at 180 degree, they turn it into nanowires as well, that we can see more in details with the TAM images. Like as you can see here, the 110 nanorods. By increasing lanthanum concentration, they turn it in the oriented attachment rods. And then the nanocubes synthesized at 180 degree up to 10%, they turn into nanorods as well, oriented attachment, but particles is smaller than the 110 degree. So after the doping Ceria nanoparticles, the Ceria fluoride structure was essentially maintained for 110, and no secondary phase was found in this series. On the other hand, for the series synthesized at 180 degree, up to 20%, a secondary phase was found, and then this is probably between the bimodal morphologies, and then also by different distance between cation and anion. And then here, as we can see as well, and then maybe the figures here of that show the lattice parameter, we can see the shift for lower angles that will prove that this fluoride is a defective fluoride structure. So here in the Raman measurements, we will see very clear this effect. As I said, the cubic fluoride is essentially maintained. The F2G peak is a peak for the Ceria materials, and then this peak is shifted to lower waves, and then we see here also the asymmetry is increased by the samples synthesized at 110 degree, and then the defects also is very clear for the samples for 110 degree. They are bigger than the samples 800 degree. So this defect is attributed to the intrinsic and extrinsic oxygen vacancies. And then in here, more in details, when we make the average of the peak of F2G and the defects, we can see the correlation and the lattice deformation by increasing the amount of lanthanum, and then this was different for the methods such as 110 and 180 degree. So this is our experimental setup for the catalytic tests. So our products was a methane and the oxygen, and then this was diluted in helium, and then was performed at 750 degree, this reaction. And this reactor was coupled in an online mass spectrometer that we could control this reaction in a very fast way, but we could see the change. So here we analyzed first the effect of lanthanum doping in the Ceria nanoparticles, how the amount of the dopant will influence in the catalyst. As we can see here, we can see the difference in the amount of the oxygen vacancies that was said in the beginning. This oxygen vacancies is really important in your CMU reaction. As you can see here, is the performance of the sample with 50% of lanthanum, that here is the spectrum in red. We have a higher amount of defects. So we can see here the conversion and then the selectivity much higher than the sample with less lanthanum. So this really affected the reaction. And as I said, this reaction OCM is still not commercialized. We need 30% of yield. That here in this first tests we made, we achieved 23%. So that is really good. Like it's up to most of the work published in the literature. Another variation that we want to test and then study the effect of the synthesis parameters. Here we have the samples synthesized with 110 degree and 180 degree. So basically we expected, I don't know, to be the same, but remember, we have a different amount of oxygen vacancies. Okay, this makes the better performance of the samples synthesized with 110 degree that have higher amounts of oxygen vacancies. But an interesting point here is that amount of oxygen vacancies had influence in conversion, but also the lanthanum was really important for selectivity. Here in the sample, if we back in the sample of with 10% synthesized at 110 degree, that the amounts of oxygen was not so different from the sample 180 degree, was like 47% of selectivity. And then the sample synthesized at 50% of lanthanum at 800 degree achieved a similar selectivity with the sample synthesized with 110 degree. But what is important in catalysis, especially in this reaction, is maintain this catalyst very stable. And this was analysis of my catalyst, of the catalyst that had a better performance after the OCM reaction. And then as we can see here, no big change was made in the crystal structure or the defects. And this is another evidence that this catalyst is very promising, because they still stable after the high temperatures, after the reagents, and then this oxidation atmosphere as well. So I will summarize briefly here the key achievements that we had in this work. So higher concentrations of lanthanum induces the selectivity for OCM reaction. Also, the creation of the oxygen defects improved the activity of the OCM reaction, possibly due to the transport in seriality, which is fundamental for OCM performance. So lanthanum doped Ceria not only result in drastic improvements in reactivity and selectivity, but shows a promising catalyst during the redox cycling, because this catalyst is still stable. So here I will show you some perspectives for this work. We had a project, a FAPES Sprint project approved to study this catalysts under inoperable conditions that would be really important. Also, we just send the samples to do PDF measurements that will give you more information of this local structure, how this strain or how this local structure will be influenced, so we can see this catalysts in a way, in atomic scale way, and we can explain better this mechanism. So also we have we still have some meetings with Dr. Cristiani from Sirius that will also be performing some inoperando measurements to study better these catalysts. So I'd like to thank my friends from Lamen, from UFABC, also from IPEN, and then all the agents that support us. So I would like to thank you all for the audience, and then I'm open to questions. Thank you.
Thank you, Fabiane. Do you have any questions from the audience? Shoot your questions. Well, I see a lot of raised hands. Ana Flávia is here with us. Please proceed, Ana Flávia.
Very nice talk, Fabiane. It's not my field, it's just a curiosity. When you mentioned about that C2 selectivity, and you mentioned about the yield of 30%, okay? So where does this number come from?
So you want to know better about the yield?
Yeah, this number, why not 40%?
No, the yield is a connection between
so there is a borderline here. So
and selected.
Yeah, yes.
Oh, yeah. And then because this reaction is not commercialized, and then most of the works is still like, maybe this reaction was studied in the 80s, was like a boom since 82 to 90. So they performed catalysts that had a performance and selectivity lower than 20%. And then they start to try different catalysts. They achieved better yields, but still none of the reported works could report a yield up to 30%. That will be more viable to the industry wants to commercialize this reaction, because lower yields of ethylene or ethane lower than 10% is not economical interesting for the industry. I don't know if I answer your question.
Okay, Fabienne, thank you.
Okay.
We have two more questions coming from the room here. Pablo Fernandez, please.
Hi, it's me again. Fabiane, congratulations for your talk.
Thank you.
I will make a question comment. I don't remember exactly the mechanism that you presented at the beginning, but I wonder how much do you know about the mechanism of the reaction? Because in your conclusions and during your presentation, you're focused on the oxygen mobility, that it is clear that it can be an important factor. But when you show the microscopy image of the particles, it is clear that you are changing a lot the surface area, and you are changing the shape. Then you are changing the planes that are exposed, and you probably are also changing the oxidation state of the atoms. So if the molecules absorbs at the surface, then you have a catalyst. All these things may play a role. Could you comment, because you focus only on the oxygen mobility?
This mechanism is quite complicated. I showed, you're right, I showed a little part, because it's like, it's still discussed that in the literature is still discussing about this mechanism. As I said, some researchers say, oh, this kinetic mechanism is Mars von Krevelen, another say another mechanism, but it is as like all the published works up to now is this reaction is really important, is happening in the surface. Of course, the surface, the planes will make this different, and also the different, that's why we want to do the PDF measurements, that we'll get to know better this local structure, because until now with Raman and the XRD, I just have a clue about the defects, but I don't really have sure about the oxidation states. If it's Ceria 4, or Ceria 3, I still don't really know. I'm not sure about this. I will be sure when I have maybe examples or Shanice and then PDF, these measurements. Also, when because this reaction, the thermodynamics is quite complicated. I have a reaction at 750 degrees, but this temperature can increase during the cycling, during when I have the methane, when I have the oxygen. Maybe this will change, and this temperature maybe is higher. I don't know. And then mostly of the works now, I think last year, some works in situ in operando start to show this, that these states that we see when I analyze my catalyst in a normal temperature, or not even in a operando or in situ condition, is different from my reaction. That's why it's really important. This work we'll do very soon, these measurements in situ in operando, that will answer the questions, because this is still a big question for us as well.
Okay, thank you. Just keep in mind that in those techniques you will get an information about the bulk, about
The
all
border.
the nanoparticle, and your reaction happens at the surface. Of course, it can be still very important, but it will not completely solve your problem. We have worked for many decades to do with this.
Oh, I know. I can imagine that. That's not the easy work. That's why it's quite complicated to choose this reaction, because it's still a lot of questions to answer. But well, this is why we are working science. Thank you.
Okay. We had a last question from Professor Juarez.
Okay, thanks, Fabio. Okay, thanks. Can you hear? Okay.
Thank you, Professor.
On your experiment, are you able to measure this oxygen concentration on the samples that you have? Do you have this information on?
Not now. We can have this information by XPS. We can maybe perform this, and then also some electrical measurements that we have been.
Why I'm asking for you, Fabiane, is if you know the oxygen concentration on the samples, and you know the composition of the lanthanum 203 and Ceria 02, and then you are able now to establish how many Ceria change the oxidation state from 4+ to 3+. For every oxygen that is missing on your sample, 2 Cerias change the oxidation state. Okay. Then, but the big problem is, like Fabio says, the following: where are located, once you have the oxygen composition, the question now, where are located Ceria 3+? They are located more closer to the surface, or they are located close to the core. Based on atomic size effects, the size of the Ceria 3+ are larger than Ceria 4+. Those Ceria 3+ are most likely closer to the surface. You have to, if you have oxygen and you know to establish where the Ceria 3+, 4+, most likely Ceria 3+ is closer to the surface because of the size effects. Or you have a lot of vacancies. Then maybe the Ceria 3+ can exist inside of the sample on the core of your nanoparticle. But I think that you have to start to know the oxygen concentration.
Yes, but also we want, that's why we need to know about the local structure, because we have the influence of the dopant. Like we have lanthanum, and then like have few works in the literature that show, like if I have lanthanum or I have gadolinium, this will change. So that's why it's important. I think it's really important we have like to get to know better this local structure, and then also to get together mixing this with the atomic model. That will help us a lot, because it's not well reported in the literature. That is a question that you have to answer.
But the point, that's my final comment. You have 2 types of vacancies on your sample. One type of vacancy is due to the lanthanum composition. Okay.
Yes. Yes.
Then you have another type of vacancy that is comes in because of your synthesis process. Your synthesis process can induce a vacancy in there because you don't have a perfect composition. If you can control the perfect composition, CO2, then all the vacancy that exists in the material will be due to this unbalanced composition of between lanthanum 2 and CO2. And this vacancy is not going to change the Ceria oxidation state because of the charge neutrality, unless you have two vacancies close to Ceria. Means if you know the oxygen vacancy that's induced along of your synthesis process, then you can able to reach the Ceria 3 plus to see how much Ceria is there. To get my point is the following: if you mix up Ceria 3 plus, if you mix up lanthanum 2O3 and Ceria O2, you don't form Ceria 3 plus. There's no way. If you mix up of them, only if you have additional vacancies.
Well,
This is a very interesting discussion, Juarez. I would be very glad to keep it, to take it further with you. And well, that's why we have those very interesting questions in all our presentations that as a chair, I let us move a little bit ahead of our schedule. But indeed, that's why we are going deeper in this vacancy and trying to know, but we can talk about later. But we have a perfect solid solution. So in principle, we know the number of oxygen. If you mean by oxygen vacancies, that's what we want to know. And the oxygen vacancies are basically given by the lanthanum doping, right? That's so we have a in principle, we have a very good solid solution. You only see one phase. All the characterizations that we perform show no segregation of lanthanum or Ceria in the samples, okay? So basically the oxygen vacancies is given by the number of lanthanum that go into solid solution.
But then how can we explain that there's Ceria 3 plus?
Ceria 3 plus Ceria's, okay, then we go to the reaction conditions, which is something else.
Yeah.
Okay. Yeah, no, that's very interesting. But this is the reaction conditions, and we have one way. I have to tell you that I have one way to answer this question. That we have been measuring the electrical transport, the ionic conductivity of those samples at high temperature. Okay, so this is a way of seeing if the mobility of the charge carriers changed, because we have measured under both air and also under reducing atmosphere, which produces Ceria 3 plus at high temperature, okay? But we have the data that shows that there are no big change between both oxygen pressure, oxygen conductivity at different oxygen pressures. So meaning that the oxygen vacancy, the number of oxygen vacancies is much more pronounced because of the lanthanum doping.
That's the situation.
Yeah, it'd be good to figure out how it is happening.
Definitely. So and only with very modern technologies, techniques, in order to really check that in the reaction control. So we are talking about 800 degrees, different atmosphere. So those are complicated measurements that we are moving to using synchrotron radiation.
Yeah.
That will be the interesting.
Yeah, we published this paper with molecular dynamics simulation I provide for you, and then we have done some quantum chemistry calculations for a mixture of lanthanum 2O3 and Ceria O2. It's a particle size not so large, but about 2 nanometers. No, it's zero. This goes to almost 1.5 nanometer. In this mixture, we started from like a amorphization phase, and we cool it down, and they have the structures. From our simulation, there's no way when we mix the two of them, they're Ceria 3 plus.
Yes. Well, do you simulate it at high temperature and reducing atmosphere as well?
Yeah, but this is the point. You model,
How many atoms?
Yeah, you are when you do it at a high temperature, you are creating some defects on the internal. those oxygens are, then you have a surface that is rich in oxygen, because this oxygen was in the bulk, but they moved by the diffusion to the surface, most probably. And then this vacancy, you give us C3+.
Yes. Well, from the material science point of view, if you have a particle 1.5 nanometers, I would say that you only have surface and you don't have bulk.
Sure, I agree with you, but it is what photochemistry does. But the temperature, I think the key point is the temperature.
Yes.
The temperature.
And the oxygen partial pressure plays a role.
The temperature, because I think somehow you are creating a vacancy on the core, because what is all simulation shows. When you do the simulate annealing, we stop at, like, for example, 800 kelvins. The simulation, there's a lot of vacancy on the core. But where is the oxygen? They are on the surface. And those of vacancies are going to give rise to the C3+.
The oxygen goes to the atmosphere.
Yeah. For our calculations, it goes to the surface because we keep them there. And then you have a rich concentration there. But if on the experimental reality, it can go soar and then you give the atmosphere. But then
it goes to the environment. Yeah. Yes. Very
good.
nice, Reyes. We'll be more than happy to discuss that with you.
Sure.
But unfortunately, we have to move on. And thank you very much for your questions. Thank you very much, Fabiane, for your
nice
talk.
All for all comments. And then I'm very happy. Thank you.